So, welcome to this session on the continuation of the time harmonic form of Maxwell's equations. So, we saw that the concept of the loaded resonance and the source free resonance and the distinction between them, particularly the loaded resonance deals with the matching aspect of the problem. It enables me to incorporate the presence of the source and thereby match the source to the load. However, the concept of loaded resonance does not give us a physical insight into the modes that are responsible, modes that are responsible for the for generating that particular resonance. So, in order to know or in order to find out the modes which are responsible for that particular loaded resonance at that resonance frequency or in the vicinity of that resonance frequency, we go to the concept of source free resonance. The source free resonance is found by applying the boundary conditions of the problem in the absence of the source. Okay. We match the electromagnetic fields and the roots of the characteristic equation give me the source free resonance. Now, in addition to what we discussed previously, these roots are not real, they are not real, they are complex numbers. So, that might seem strange to you because we are always accustomed to think of resonance being a real number. That is, if you would simulate a structure in HFSS and things like that, you would imagine that the resonance frequency is coming out to be real. But no, if you actually would follow the strict rigor of the analysis of antennas, you will discover that the characteristic equation, the roots from the characteristic equation are not real, they are complex. This has to be realized. Why this has to be realized? Because if I qualify these roots as omega r, I will write this as omega r prime plus j omega r double prime. So, this is the real part of the resonance frequency and this is the complex part, the imaginary part of the resonance frequency. You have to also understand that any kind of radiating structure, any structure will have a imaginary part of the resonance frequency. Okay. Not only that, the quality factor of the antenna will be given by omega r by 2 omega r double prime, the real part of the resonance by twice imaginary part of the resonance. So, why this quality factor is important? Because we want to excite modes, let us say, to couple with another mode. Let us suppose we want to have a structure in which we have two resonances. These two resonances by mode 1 and mode 2. So, that is my mod S11. Okay. So, this is a dual band structure. So, minus 20 dB let us suppose, and this is 0 dB. So, this is a dual band structure. Now, suppose I want to make these modes come close together and combine to make a broadband structure. So, in order to make this happen, I will try to identify modes which inherently have a low Q factor, because a low Q factor means the potential bandwidth of such modes is inherently high. So, we want to have modes which low Q factor, okay, which have also a high radiation efficiency. Okay, a high Q mode might look like this, a low Q mode will look like this. So, it has potentially a wider bandwidth compared to a high Q mode. Therefore, it tends to combine with another resonance in order to give me a broadband behavior. So, therefore, you see that how the source free resonance is very, very important, because all this picture is obtained from the knowledge of the modes which is coming from the analysis. So, it is very important. Okay. So, therefore, this is the idea behind the resonance nature, which is first starting, which has its roots embedded in the power conservation equation. Okay. We will just simply also explicitly tell you a little bit about the nature of the feeds in any realistic structure. How does the feed affect the matching problem, practical, from a practical perspective. So, let us suppose I have a patch which is excited by a coaxial probe, and I have the same patch which is excited by a slot coupled feed. So, you see that this feed has two different it uses two different kinds of substrates, RS1, RS2, while I have only one kind of substrate here. So, this is the ground plane, this is the microstrip line, and this is the slot. So, see, after you have done this kind of, what is the comparison between the probe fed patch and the aperture coupled patch? After you had made the design, the probe fed patch cannot be changed, because you have made the design in HFSS, you are stuck with that design. If you get a little bit fabrication error, as you will always get, tolerance, due to tolerance your design, your fabricated design will change from the simulation design. Okay. So, there you are stuck, because you cannot change anything after fabrication. But therefore, you see here also you have to drill a hole through the substrate, and this length of the probe will lead to the probe reactance. As I told you, the difference between loaded and source free resonance, if you look at that, if you look at the slide, if you compute the, let us mark here, if you compute the source free resonance of this kind of a structure, which is excluding the probe, let us say this is a dielectric resonator antenna, and you have computed the source free resonance of this, and you have also performed a simulation with the probe and found out the S11. So, that S11 is here. So, this is the resonance. So, this is the loaded resonance which is with the probe. This is the loaded resonance with the probe. Loaded resonance. Now, when you calculate the source free resonance by applying image theory, as I said, and take this as a whole sphere, and without the presence of the probe, then you are going to compute the source free resonance to be here. So, source free SF, and this is the FL, which is the loaded resonance. So, the source free resonance will differ from the loaded resonance in general. In fact, at a particular loaded resonance, there can be, it can be contributed by 2 or 3 modes which are located close by. Okay, the radiation at this point can be contributed by this mode, it can be contributed by this mode and this mode in conjunction with each other. Now, the next question is how to find the relative contribution of this mode and this mode, how to calculate it. We cannot get this by simulation. How to calculate it? We will come to these aspects when we particularly deal with the modes. Here I will give you a rough idea, but before that we will talk about this one, as we were talking, that your probe reactance is going to shift, it is going to cause a shift in from the source free resonance. So, your source free resonance is what you identify, that this is the resonant frequency I want to design this patch in. But when you actually design the patch, due to the presence of this probe reactance, your resonance frequency, that is the frequency at which the S11 is giving you a dip, this resonance frequency is going to shift, this Fr is going to shift from the source free resonance frequency. However, for this design you see that one of the like drawbacks of this design is that it is using two substrates, and substrates are like a costly business at microwave frequencies. But how does this accomplish the match? You see this length of stub, this is called stub. It is an open ended transmission line. So, this substrate is not ending here. So, this is the substrate below the ground plane. So, this stub is used to match this patch with the feed line. So, even you can post trim after you have manufactured this, after it is fabricated, you can maybe trim this a little bit in order to fine tune your match. So, you have the flexibility of adjustment after the design. In addition, you see that while this probe so, while this probe radiates, the thicker the substrate, the larger the length of the probe, the stronger the probe reactance, effect of the probe reactance, and the more the probe radiation. But here the slot length does not depend on the thickness of the substrate. So, it is less susceptible to vary the inherent patch resonance. It is not that the slot does not radiate, the slot also radiates and it causes spurious radiation, but the spurious radiation from the probe is larger because it is dependent on the height of the substrate. In addition, you have to drill a hole through the substrate, there is no hole to be drilled here. So, all these features contribute to the positive sides of this design. So, this is how the resonance phenomenon play an important role in the practical design of the circuits. In addition, you will see that the feed radiation, this is the feed, and the feed radiation is shielded by the presence of this ground plane. So, the effect of the feed radiation does not come there, while the feed radiation is an important part here. So, besides the shifting of the resonance, the effect of the feed radiation and everything, so it is you have to make a judicious choice versus the simplicity of the design, that you are using a single substrate here. It is not that the probe coupled design is not used, it is very popular in antennas, in antenna design. So, it is very popular in antenna design, so as the aperture coupled. It depends on the situation you are at hand and the amount of money you want to spend, and the other factors which you may or may not want to mitigate. Okay. So, the resonance behavior plays a very important role in these in the practical implementation of the circuits. I will now describe to you how the concept of power, where is the concept of power flow, as we were discussing, the E cross H star, the real part of E cross H star, where does it, how do we use the power flow? Besides its various use, that is like finding out the power flow through a surface in numerical problems, but one very important thing is that I will take the same problem, let us say a microstrip coax fed microstrip patch, probe fed microstrip patch. I want to find the power radiated, or a dielectric resonator antenna. I want to find the power radiated. So, I will surround this by an imaginary surface and find out the integration of S dot ds over the real part of S dot ds over this surface in order to find out the radiated power. Okay. So, this is how we can find out the power radiated by an antenna. In a waveguide scenario, for instance, I am exciting a mode in a waveguide and I have a receptor here. I am collecting the power here. So, the power is travelling down and this is listening to this power or listening to this wave. So, this is the electromagnetic energy is coupled here. So, this is the exciter and this is the receptor or the receiver. So, here you, because if this receiver or the receptor or the receiver is there in the far field, I need to only calculate the radiated power from this probe. I do not care about its reactive part, because its reactive part does not reach this far field. However, the reason we spent all this time to discuss the reactive part of the power, to say that it is contributed by the imaginary part of the complex Poynting vector and the stored energy term both together, which is a purely real number, is to match this excitation or the source of excitation to the waveguide, because for matching this I will need to tune out the reactance here. So, the input impedance of this probe is very vital. Finding the input impedance, in order to find out the input impedance I have to find out the near field of the probe. How does the probe, what is the reactance of the probe, the resistance of the probe, the total impedance of the probe, the complex impedance of the probe which is exciting this waveguide. So, that is where the input impedance plays a very vital role in the excitation, and when we are receiving, when we are getting the received power, in order to find out the power received we have to again calculate the power received using the Poynting's theorem. In additional cases, for example, this kind of case, as I said, we might have a resonance here, mod S11 versus frequency, and I may be interested to know if there are multiple modes nearby. As I told you, which mode, so mode M1, mode M2, mode M3, which is contributing which kind of power here, how much power, whether mode M1 is predominantly contributing here or mode M2 is contributing here or mode M3 is predominantly contributing here. So, I want to find out a chart listing at this resonance frequency Fr how much power is being contributed by all these modes. How do I do that? We will come to what we call the Green's function of this problem when we discuss the magnetic current source, okay, and the source problem, okay, inside in the wave equation, and there we will see that the solution to this problem is obtained through the input impedance is obtained through the Green's function. And what is the Green's function? So, the Green's function is particularly, just to give you a rough idea, it is if I take a unit impulse source here, I find the fields due to this unit impulse source. Why do we do this? Because I do not know the current on this probe to start a priori. It is like giving you a circuit like this with two resistances R1 and R2, 5 ohm and 10 ohm, and asking you to calculate the current without the battery being unknown. This is the battery which is driving this network. I have given you the boundary conditions here, and if there are any other layers, the boundary condition at the probe itself. Those boundary conditions are like the resistances, but this is microwave frequency, we do not have resistances, we have boundary conditions. But I have not told you what is the current flowing in this probe. So, without this information you will not be able to calculate the fields. So, in order to start the process, we need to assume the source of excitation, and that source of excitation is the unit impulse, and from that unit impulse I find out the radiated fields by applying the boundary conditions on the probe and by applying the boundary conditions on this surface. We expand the fields inside the probe, okay, and we expand the fields inside this antenna structure, which is also called a dielectric resonator antenna, or DRA for short. And we break up the problem into two parts. One is called the particular part, another is called the homogeneous part. The particular part is the part where I have only the source present. The source is radiating like this. So, this is R is equal to 0 and this is the source radiating. So, the source will be broken up into, source current will be broken up into two components. So, if this is the z direction, so if this is the current in the z direction, this is broken up into the theta direction and the r direction. So, this is the particular solution. So, this is your ground plane. The homogeneous solution is, this probe is absent, it is not there, and you have the dielectric resonator. So, the boundary conditions of the problem work without the presence of the source. So, this is the homogeneous solution. In reality, this is the particular solution with applying the image theory, removing the ground plane, and This is the homogeneous solution removing the ground plane and applying image theory. So, this is after applying image theory. From here applying image theory, from here applying image theory. So, the particular solution, the response of a source here, response of the source here to this probe which is considered as a boundary, that response is called, it is encompassed or it is the information is contained in the particular Green's function named GP, and the information regarding this boundary without the presence of the probe is contained in the Green's function labeled GH, the homogeneous Green's function. These two Green's functions are added together to form the total Green's function G. How does it happen? We will again discuss it in more details, but now roughly we match the basic thing is that expand the fields, write down the potential functions involving the modes, step 1, expand the write down the fields from the potential functions, match the fields at the discontinuity. In the case of the particular solution, the discontinuity is located at the source, so you match the fields across the source. In the case of the homogeneous solution, the discontinuity is across the dielectric surface, you match the fields at the dielectric surface. So, this Green's function is going to contain a summation, an infinite summation over the modes. Now, if I want to find the current on this probe, however, I do not still know the current on the probe. I know that if only a source is present here, a point source is present here, what will be the electric and magnetic fields due to this point source and the presence of this probe only immersed in a material of permittivity epsilon r, which is the same as the dielectric resonator material. That information is in GP. I remove the probe, I cast away the probe, have the dielectric resonator only present, and again the response is contained in this term GH, but I still do not know the current on this probe. In order to find out the current on this probe, I have to find out, as I said, GP and GH, add the two, find the total Green's function and apply the Pocklington's integral over the probe, and that is E incident on the probe plus E scattered, which is the Green's function times Jz, because the current on the probe is along the z direction. So, this is the z direction. So, this is Jz times ds prime, that will be equal to 0 on the surface of the probe, because the probe is a conducting surface. So, this is the probe. This is a conducting surface over which this equation is applied. I know this, which is G Jz Ez, that is due to Jz, due to a z directed current flowing here. What is my Ez? Because the z directed current is going to produce an Ez. So, this contains the cause and this or the source, and this contains the effect. That is the grammar of the Green's function. So, this equation is called the Pocklington's integral. This is the Pocklington's integral equation. This is fed to the method of moments. This is fed to the method of moments, okay, which solves for this unknown current Jz. Essentially, we take this probe surface which is here and break this up into piecewise sinusoidal basis functions. So, we evaluate the unknown currents in each of these basis functions. By applying the Pocklington's integral equation over each subsection. So, for this subsection, for example, the current I 1, the electric field due to the current I 1 plus the electric field due to the current I 2 plus the electric field due to the current I 3 plus due to I 4 plus the electric field due to the current I n is going to be 0 added with the incident field. This will give me the first row of the equation. Okay. So, anyways, so I will using the method of moments it will be solved. We are not going to the details of the method of moments, but right now it is important to know for us that this current will be solved using the Pocklington's integral equation, where after the Green's function is found out. Now, the most important thing here is after this current is solved, I can make this equation work in reverse gear. What is called making this equation appear in reverse gear? I told you I want to quantify the amount of radiated power due to these modes. What are the power radiated by these modes at this frequency? In order to find out that, once I have evaluated my current, once the current is evaluated using the, once this is found, once this is obtained from the Pocklington's integral equation, I can find out G Jz ds, because this current is known and this Green's function is known. This Green's function is a summation over all the modes, as I told you earlier. So, I can stop this Green's function if I am interested in one particular mode. I can stop the summation in the Green's function and make it applicable for only that mode and find out the radiated field due to that particular mode. Okay, so, if this is Jz Ez, this is going to give me the scattered field EZSC. So, this is the scattered field EZSC. Once this Jz is known, I can integrate with any relevant Green's function and find out any relevant component of the field. So, I can find out my radiated field at this imaginary surface. As I told you before, I can find out the radiated field at this imaginary surface for one particular mode, because I have already the Green's function and I know this probe current. The Green's function is a summation over all modes. Convolving the Green's function, this process is called convolution. This process is called convolution. It is called convolving the Green's function with the probe current. So, once this Green's function is convolved with the probe current and I can stop the summation of the Green's function at, restrict it at one particular mode, convolve this with the probe current, I can find the scattered field due to that particular mode. And therefore, I can find out E cross H star. I can find out E cross H star, or real part of E cross H star, real part of E cross H star double integral ds for that particular mode, and thereby I can quantify the power radiated by each of these modes, and I can have a chart showing at this point what are the powers radiated by the individual modes and which mode therefore is dominantly contributing to the radiation here. So, these are all applications of how I use the Poynting vector in the efficient design of guided structures or antennas. Okay. This is the basic idea here is not to go to the details of how the Green's function is found out. It is an elaborate process and it runs through hundreds of pages, but that is not the main point. The main point here is how the concept of the power, the Poynting vector, enables us to find out, design better devices, and not only that, to give us a deeper insight into the design of efficient devices. We do not want to be like a try by luck, that I want to like design one particular, make my antenna work at particular design frequency without any clue as to what is happening to the modes and how much power is being coupled to the desired mode. I can have a quantitative estimate, nothing qualitative, a quantitative estimate of the power radiated at different modes, and it will give me a rigorous perspective, because there is no approximation in the Green's function. It is a rigorous technique, it is a full wave technique with no approximation. I mean, there are a couple of steps in it, and any mode, any method will have a number of assumptions in that sense, but otherwise it is a very full wave and rigorous technique. Okay, all the modes are considered and everything is taken into account. So that way I can find out the, I can have greater insight into any given resonance, or as is here, a deeper insight into any given resonance of an antenna. Okay, so thanks for your attention. So we stop here.